Yeah, thanks for having me. Thanks, bayerninnovativ, for organizing a very interesting event, very interesting discussion we had. I have the honor and pleasure to introduce our company, Astyx Satcom, to you guys, on technology we are working on, and also what we are doing towards 6G and NTN. Quick snapshot of the company. We are kind of a startup, so a young company that was formed in the current version in 2021. So basically, a bit more than a year ago. Some of you I know from the morning's discussions know us already. If you've been involved in radar, you might know Astyx as a name. We're basically a spin-out of a bigger group in the past, whereby the radar business, so millimeter wave radar sensor, was the core activity, and that was acquired by Cruise, so the autonomous driving company, autonomous driving subsidiary of GM, basically 2 years ago. And this company, or the part of the company that's dealing with Satcom and RF links, has been set up as an independent company. Yeah, we're starting with a young team, good mix of experienced guys in the RF technology and some younger folks. Right now, it's around 20 employees, majority of those for such a tech company in R&D and manufacturing. We have very nice campus-style headquarters in Ottobrunn, so right next to Airbus. So if some of you have interaction with ESA Aerospace from time to time, let me know. We are basically in the same building, so we are sitting next door on the upper floor of ESA Aerospace. We enjoy in this campus lab space and office space on the same roof. We are controlling the entire production and manufacturing chain, even back to microassembly, die attaching, and back to the substrate manufacturing, which helps us a lot in ensuring high quality and implementing or developing ambitious things like Q-band, V-band, coming to that later. There's US subsidiary, of course, ISO certified, and so on. So what are we doing? It's basically core technology for NTNs for satellite communications. So we are dealing with high-power amplifiers, in particular with linear amplifiers. I'll come to the technology part in a minute, but of course, let's start with the market first. So where is this used for? And you already have seen this from the previous presentations. Of course, satellite communications is everywhere. It's an integral part of our lives. If you're watching TV, if you're watching news, of course, news are being broadcasted via satellite. If you see footage from Ukraine, so quite recent occasion, if you have any weapon system you can think of, it doesn't matter if it's for comms, for operations, if it's for surveillance, or if it's a rocket or rocket defense, the weapon itself, it will need satellite connection, because the chance that you have a fixed line out in the field is pretty rare at the end of the days. And users these days, or consumers, as we have heard from Oliver before, they're getting used to ubiquitous bandwidth and basically high bandwidth internet connection on mobile devices, no matter where you are. It doesn't matter if you're on a plane, you want to watch a movie on Netflix, or surf on the internet if you're on your cruise ship vacation, or if you're on a train. Maybe that's a bit different situation here in Germany from time to time, but the consumer these days is demanding high quality internet and data connection everywhere, basically. And this includes rural areas. So I think we all know Starlink, of course, with their recent launch, direct to consumer broadband connection. The same is, of course, coming, or is already there, is launching for enterprises, enterprise buildings, or commercial real estate areas. Starlink has quite recently, I think 2 weeks ago, launched their maritime service for private yachting, so quite affordable, so that even if you have a small boat or you're on a caravan or whatever, you can use their mobile dish satellite. Of course, we have the whole thing of IoT. I think that's pretty known to this audience. So you have sensors in the field that needs to communicate. You want to stream data out. You want to apply edge computing. You want to run AI on the device. You want to do over-the-air updates. All these use cases in the industry 4.0 sector are requiring some kind of communication link. And of course, as Rainer has explained earlier, so I'm not going into detail, your mobile backhaul. And that's where we're coming to talk about 5G, 6G. We had the technical evolution earlier on. Basically, in the next 10 years, there will be 3 billion new users connected to the internet. And many of those will be in rural areas that don't have a connection, or that where it's going to be a challenge for your 5G, LTE, and 6G mobile station to get it connected via fixed line. Yeah? So that's where satellite networks come into play, as we have heard earlier. And then there's the future. So again, I can skip this part. I think that was well covered by Oliver earlier. Interior, infotainment, connected car, the big cinema screen in the vehicle will be a key differentiator for guys like BMW, Daimler, and other OEMs in the future. This is where differentiation takes place, and of course, connectivity and broadband and quality of connection is a key part of that. And we have also other, just a selection here, other very demanding applications coming up. Let's say augmented reality, for example, where you want to do overlays over the real world, very latency sensitive, or the current hype metaverse, diving into the metaverse, virtual worlds. Lots of new applications that requiring bandwidth and high broadband. So we all know what I call the NGSO, so non-geostationary orbit revolution. We have a lot of new satellites connections coming up, like Starlink, OneWeb, Amazon Kuiper, and so on. So there's LEO, but there's also medium Earth orbit. So things like SES is launching. We have other constellations also in the more traditional GEO orbit with very high throughput, like Hughes, Jupiter system, and these kind of things. At the end of the day, again, it's all the same story. Ubiquitous internet connection everywhere in rural areas, high bandwidth, high number of users, high number of spot beams, and in particular, if you talk about LEOs, low latency, of course. I mean, I know there's discussion about what of this is realistic, and there's like Elon, we all know Elon Musk, like he's operating and communicating, but the development for so far is taking place. We're expecting up to 50,000 new satellites being launched over the next decade. Multi-billion-dollar investments, capacity increasing by more than 10x, up to more than 20 terabyte per second over the next years. And of course, this is all enabled by a whole new space ecosystem that we're seeing. Guys like Era Aerospace, micro launchers, Cube satellites, and the whole part of the ecosystem that these are benefiting from. So what does it mean for us? What does it mean for Satcom? Of course, these kind of constellations have very dedicated system requirements. So in a simplified way, of course, the key part, what you want to have is a maximum throughput. You want to have a high bandwidth, high number of spot beams, many users on a satellite, broad coverage, all these kind of things. Means for us as a Satcom, as an RF company, of course, maximum RF power out. Yeah? Maximum performance there, so power out so that you get more information, more signals on there, higher bandwidth, better signal quality, less noise, less or more stable gain and phase on the signal, just to get more data out. And of course, these LEO constellations are set up, you know this, in a very decentralized way. So lots of small satellites that are not built not for 15 years in space, but maybe for 5 years. And then have implemented deorbiting mechanisms. They want to have very many small decentralized gateways. They want to shift capacity around the world, shift around weather, shift towards demand, these kind of things. So also means that the gateway structure needs to be very much decentralized. You need small systems, scalable systems. You go towards smaller antennas, smaller amplifiers that are directly attached to the systems. You have good pointing performance. And of course, if you're talking smaller antennas, tendency to go higher frequency bands. Again, congestion is an issue in the current bands. Interference becomes an issue. So Elon Musk has some public fights going on with other companies fighting about 12 gigahertz frequencies, and you probably have seen that quite some weeks ago. So there's also push towards higher frequency where more parts of the spectrum can be used. And of course, operating costs. Yeah, these networks cost billions and billions of dollars. So investment in TCO is of course a key factor. So what you're demanding from the gateways, from the network, from the ground station is basically high power efficiency, low operating cost, high robustness, broad range of operating conditions. And you can also go towards the more remote places or more extreme places on Earth. We are solving this with help of our amplification technologies, which is very much centered about linearization of the signal. So now it becomes a bit technical going through theory. Again, this will be known for some of you. This is how, on the left side, how an ideal power amplifier would look like. Yeah? So it's a linear amplification behavior, meaning you have a proportional relationship between power in and power out. So gain and phase are basically constant over the spectrum. This is what you want to have, and then you're operating the amplifier basically at this point, which is the saturation. After that, you don't get any more power out. What happens in reality on the right side is basically you have this linear region where power in is proportional to the output power of the device, and then at some point your amplifier becomes non-linear, unfortunately. So this is the trait of any amplifier you have out there, no matter what it's doing. And this is typically where you want to operate your amplifier. So this is the maximum efficiency, or operating point of maximum efficiency. And what you need to do in order to get to this linear region is to back it off, meaning to reduce power. Otherwise, your signal would be destroyed. Yeah, if you have this kind of non-linearity, it negatively affects the signal quality. You get bit errors, your intermodulation curve goes down. In a nutshell, you have less data bandwidth you can get through the system, so you have to operate it basically at a not ideal point. And this is exactly where our technology is coming into place. So in a bit simplified way, what we are doing, what part of our modules are doing is basically pre-distortion linearization. So you have a certain behavior of the amplifier, which we've seen earlier, which is nonlinear, and then you have a linearizer module, which is basically counteracting or creating exactly the opposite of the amplifier's behavior. And this is offsetting the linearity, so what you would get out ideally is, again, this linear relationship and more linear power, which is the key parameter for any amplification system and for the gateway talking to the satellite. Yeah. So this is comparable in easy words to glasses, basically. If you have an issue with your eye quality is deteriorating, you have to wear glasses, your focal length of the eye is basically not matching, you don't see sharp. What you're doing is you wear a lens, so either glasses or contact lenses, which have the opposite property of your eye, and as a result, as you all know, you can see sharp again. This is what we are basically doing to the signal. As a result, if you go back to this amplifier curve in the beginning, it's very simple. We get more power out. Yeah, so instead of operating the amplifier here, where you reduce the power, you can shift you have a more linear amplification behavior, and you can operate it here, which means much more power, up to 6 dB. So we're talking about 4 times the output power that we are achieving without this technology. And of course, this is of key interest to any gateway provider, anyone who works on this kind of systems. So it's more power out, better signal quality, meaning more carriers, more channels in the system, broader frequency that can be used, less noise, basically at the end of the day, more data throughput that you can achieve, and also some other side effects. So less thermal load on the system, higher power efficiency, up to 2 times improvement in power efficiency, and also that means lower cost on the investment and the operating side. Of course, besides smaller size and form factors, again, if you're talking about smaller, more decentralized LEO gateways, these are all the things. So if you look at this and you look at the requirements from new satellite constellations, this is basically part of the solution to their problems and what they are demanding from modern gateways. This is how the product, or part of the product, looks like. So there's quite a range at the moment. Good thing is we have built it as a modular approach, so we are able to provide anything from like the core of the module, which is this linearizer module we've talked about earlier, up to entire mini amplifier systems, which create up to 40 dB of gain, meaning which is basically an amplifier in itself, and the entire RF chain in front of the tube or in front of the antenna. So we've seen these antennas in the morning at DLR. The amplifier is basically typically, you try to minimize the distance between the amplifier and the antenna, so quite often directly mounted these antennas onto the back of it. Products are available for quite a range of these applications in RF Satcom, so both for semiconductor-based amplifiers and also for traveling wave tube amplifiers with higher power levels. We are offering standard products and also very much tailored, customized solutions for specific customers. We're working on all frequency bands, starting with C band, going up to V band, coming to that in a second. And the company is, despite its young age, because we have this heritage and we have a team that's been working with technology for quite a while and are experts in the field, we have quite nice commercial traction. We are working with the key players in the RF Satcom industry here, the big guys from the US, but also Actia, for example, in France, or Spacepass in the UK, and the Satcom here in Germany. So the gateway and amplifier providers around the globe, so to say. Yeah, we have in-house production and lab facilities, so that again is very helpful to go up the frequency range, to go to the smaller structures, and of course we're talking about satellite infrastructure. This is critical infrastructure. That means we have the highest requirements towards quality and robustness. We basically can control the entire process from initial simulations. We have simulation experts for RF behavior up to production and automated test environments here. We can provide on-site support in Europe and the US, so there's a small US subsidiary as well. And Asia not so far, but could come in the future or occasionally, so to say. Now coming to 6G or 5G, 6G for us. Where's Satcom today? Satcom today, also if you include Starlinks or you include current LEO, MEO constellations, most are operating on Ku band and Ka band. So that would say is currently the volume market, and that's where the market is at the moment. If you recall the operations control center this morning in DLR, you could see that it's basically communicating as S-band link, and the Ku band link was on the screen. Many constellations are on Ku band Ka. That is working fine, but it's running against a limit, of course, in terms of the bandwidth available. And available frequency is basically a key bottleneck for these kind of satellite constellations. So, for example, in Ka band, you have a bit more than 2 GHz of usable frequency. In the Ka spectrum, you also have governmental or military reserved frequencies. What you can use is actually limited, so the numbers of carriers and channels you can put it there is a bit limited. And also congestion is becoming an issue. With the sheer amount of satellites that Starlink or the others are planning to launch, you're interfering with GEOs, with other orbits, and it's becoming tight in that spectrum. So of course, for us, the direction is clear. It's moving up the frequency ladder. Yeah? So we're talking Q band, we're talking V band, we're talking W band. A little bit. Maybe let's start with W. Is not so much in focus for us. We've done that in the past for military. Issue is a bit, again, weather and atmospheric attenuation, so then we run into pretty similar challenges than we're seeing with optical links. V-band typically around 47 to 52 in the uplink and 43 to 46 in the downlink. And the benefit is clear. If you have a higher frequency, you can put more information on the signal. That's one. You have, again, smaller antennas, nice side effect. And in particular, the frequency band that you can use is higher. Yeah? So you can here make use of 5 GHz. You have a higher spectrum that can be taken into account. Of course, weather is an issue, so the attenuation from atmosphere and water vapor is higher in this frequency range. And also the structures, of course, become much smaller. It proves some challenges on the RF side, on the assembly and the semiconductor side in particular. Again, good for us. We've seen lots of new examples here. So V-band is a growing market. It's just about to ramp up. Here, first examples are Eutelsat in use, and also Starlink has a lot of filings already for V-band. For us, we are very happy about this because we are mastering the RF behind it, so we can deal with the smaller structures. And of course, if you have high attenuation, that's something where you're happy about a bit more power, and we are increasing linear power at the end of the day. So this is also why we have one of the funding calls from the Bavarian government, BWE. So thanks at this point also to Kimberly and colleagues. It's a joint project we're doing with one of the market leaders in RF measurement equipment and network solutions, which also has many participants here today. So looking forward to that project. Just started. Where we're developing also V-band and Q-band, very broadband amplifiers for next generation of feeder links for satellite networks on a semiconductor basis. So V-band SSPA, broadband approach. And this is, Bavarian project made in Bavaria, and something that's important to me personally, and also that's our ambition as a company. If we look at our customers, the Satcom industry is very much dominated by big US players living from large governmental contracts. And we want to become, it's our ambition to build a European space infrastructure and Satcom infrastructure, and we are at the core part of the tech stack and want to become part of this. So happy about this collaboration here, and happy to collaborate with further players in Germany and in Europe at this point. Side effect, if we have a few more seconds, just as a side note, since we have seen the Columbus module this morning, or a model of it, also our focus is at the ground station, so it's mostly the uplink and the gateways talking to the satellite from the ground, but we also have had first projects in space, first space heritage that's coming, so some of you might have heard of the ACES projects. It's basically where two atomic clocks, a French and a Swiss built, are being brought into space and are being attached to the Columbus modules, so to auto platforms here, communicating to a broad network of gateways on the ground, which are operating their own reference clocks. And of course, the goal is to do fundamental research about microgravity on these atomic clocks, about Einstein relativity theory, time dilatation, these kind of things, and also future metrology and the impact of precise or super precise clocks on Earth observation. So that's something that we're very proud of, that we've built the RF link. So it's a Ku band, I think, and S band links on these atomic clocks talking to the ground station made by Astyx Satcom. We're done with time. Thank you.